Anand.
Fine, sir. Fine.
So, did you talk to Mr. Dubey in Calcutta?
Yeah, sir. I had discussion with Mr. Dubey, and he said that stimulation type of uh, they do not provide stimulation, sir. Simulator.
Okay, we will talk about this later
Uh,
after the class.
okay. Okay. Sure, sir.
So, first, let me introduce a very key concept here, uh, and that is just log addition. Many of the students who attended my last semester class on the industrial hygiene, they know it. And I think many of you also know it. It's a very common problem, but it's needs to be understood very clearly that whenever we express anything in log form, the pressure they are actually squared. The RMS pressures are squared, and they are actually expressed with reference to some 20 micropascal pressure. We take a 10 log and find out the decibel format. Decibel format. The general expression for the purpose of addition, because we all add, we all measure in dB, unfortunately, because that is to simplify the entire thing. So your sound level meters will give you in dB, and you cannot just go on adding dB plus dB like that. You cannot do that. If you have some kind of chart, a table kind of thing, then also you can have some approximate values. But if I give you some decimal values, it will be difficult for you to rightly, find out what could be the result. Previously, when the computers or calculators or these things were not readily available, people used to use charts available for addition of this. Then and now, let me ask you a simple question which we discussed in the last class. So if I add 90 dB dB plus 90 dB, then what is the I mean resultant value if I add 90 dB with 90 dB?
93 decibels.
93 decibel is the uh, value. That means it goes only by 3 dB. 3 dB. So if in case, so when you know these values, you can add, you should have a generalized formula for doing all these things. See, now if I tell 90 plus, 92 dB, then it becomes, not so easy. So again, you have to do certain calculations. So the general expression is this. That means the total pressure level. This is L. This LP means total pressure. Total pressure level. This is
Hello,
total.
sir. You are not sharing a
Yeah.
screen, I think.
Oh, I am sorry. Oh. So sorry. Oh, I am not sharing screen and I am talking to you. What bad, very bad. So I was. I forgot to share screen. Just. Yeah. So this is the general expression. Yeah. This is the general expression. That means in terms of dB, if you express something in as L1, L2, or like Ln, then n number of sounds in terms of dB can be added as LPT. This is actually total sound pressure level, or we can say total SPL. Total SPL. Total SPL. Remember that it is in level. That means with reference to something, and it comes from the basic concept from here. And since the entire derivation has been done using this relationship, that's why the 10 log has been used and 20 log is not there. It is 10 log. I'll show it very quickly how it is done. But this is the general formula. That means you have to remember that you have some three values, like say L1 equal to 85, L2 equal to 87, L3 equal to 91. So if you want to do it, then you simply do it like this, that the total sound pressure level equals to 10 log 10, and then 10 raised to the power L1 is 85 by 10 plus 10 raised to the power 87 by 10 plus 10 raised to the power 91 by 10. As simple as that, and it's absolutely correct. It has no other problem. Now the question is that, just to have an idea how it has been derived, I'll show you here. From here, I think I was writing that. Yeah. So we know that, you can see the whiteboard, no? Something written on that part.
Yes, sir. Yes, sir.
Yeah,
Yes.
right. So now see, here you see we expressed, in terms of sound pressure level. How do I do that? 10 log, and then this is a p square by p ref square. These are instantaneous values. So what happens? You take RMS value and then put a square there. So that can be added. That can be added. But unfortunately, our sound level meters will give will give this value and never gives this value. That is the issue. So since in everywhere this dB throughout the world it is used, and nobody will give you the absolute pressure and calculate the entire thing and find out the dB. Nobody does that. So what do? We express the entire thing in terms of dB. So now now if this is the relationship, then we can write that 10 log 10 is L1 by 10. So from there we write that P1 square divided by P ref square equals to 10 raised to the power L1 by 10. This is the basic thing. Now we said that these things are allowed. That means in square format you can add the pressures. You can add these things. If you do that, then you divide the both sides with the reference pressure everywhere up to n. So now we know that this value is 10 raised to the power L1 by 10, 10 raised to the power L2 by 10, 10 raised to the power Ln by 10. If that is so, then what we can do? Now again we should try to express this in terms of dB, so that the entire thing is solved, because they are all in dB. L1, L2, L3, they are in dB. So now we rewrite the thing, go back, 10 log P square by P ref square equals to 10 log, then within bracket 10 raised to the power L1 by 10 plus 10 raised to the power L2 by 10, like that up to 10 raised to the power Ln by 10. This is the general form of adding the sound levels. This side is total pressure level, LPT, that's all. And then you get this relationship which we derived. This is widely used for many purposes. I mean, the basic concept is that, say you are standing at a point with a sound level meter, or we want to know what is the sound level at a particular point, at a receiving point. So we call it R, is a reception point. And we are listening to several sources. Let us say S1 is one source, S2 is another source, and they are coming like this. There is a trick here, that there is something which I am not telling you, that when sound waves travel from S1 to R or S2 to R, and if this value at this particular point, very close to the source, if the measurement is L1 and close to the source is L2, not necessarily that you will get the same values here. That means L1 and L2 here will not be the same as the L1 and L2 here. What is the reason? I mean, what could be the reason? Please, not the MTech students, the second year students, any of them. Means The value was this L1. Say let me write small L1. I am telling that this is smaller than L1 usually. L2 why?
Energy dissipation.
One second, please.
Energy dissipation.
Energy
Dissipation means lowering.
dissipation. Where?
Because its basic intensity, we say, it diffuses over long distances. Maybe.
Along the why? I mean, where the energy goes.
So there might be some
Heat.
obstruction, maybe.
Heat.
I give you no obstruction.
Heat.
Sir, the area over there increased, so the intensity decreased.
I am not talking about intensity. It is sound pressure level. It is the
Sir,
pressure.
maybe because of the resistance.
Resistance of what?
Air.
So the rho C, yesterday you told us.
Right. There's some audio issue, with somebody. Please check. So yeah, so the idea is absolutely correct. There is an impedance in between because there's a medium. There is a medium. So when the oscillation, this oscillation proceeds like this, then it tries to overcome the inertia of the medium, and some of the energy, because it's nothing but sound is nothing but mechanical energy. So some of the energy will be dissipated within the medium, because the sound energy sound waves will try to overcome the impedance of the medium and reach the other places. So during traveling, there are a lot of reasons for which there will be a phenomenon which is generally known as attenuation. This we'll be learning in details later. So one of the reason for attenuation is atmospheric absorption. Atmospheric absorption. There are other reasons, as you have rightly said. There will be reflection, refraction, and then barrier means obstruction. Many things will be there. Let's see that after the atmospheric absorption, we are coming to one place, one particular point, and where there are two values separately we measured. Like we switched on one source, that is S1, and we measured that the sound level was L1. Now we switch off this and switch on another source, that is S2. And due to S2, we get L2. Okay. Now we switch on both the things. That means now L1 and L2 both are coming. Now L1 and L2 both are coming. Means both are present at this place. So there is the question. Then what are sound level meters in a laboratory setup, and in an ideal setup where there are no other phenomenon which is disturbing our measurement. That is an ideal condition. So can you tell us if this S1 and S2 is switched on simultaneously, then what will be the resultant pressure? That I want to know. Just tell one, because you know it. Anyway. Now we add L1 and L2. Their levels, their SP, sound pressure levels, SPLs. If I add them, then what will happen? What will be the value? Anyone? You know it. Just now in the previous slide, you have seen it.
So it's 10 log. 10
Yeah,
to the
10 log.
10
10
to the
log, 10 raised to the power, L1 by 10.
L1 by 10
Plus
plus
10 raised to the power L2 by 10. Okay, that's as simple as that. Now, Sometimes what happens that we have a reverse kind of problem, that we measure when things are running simultaneously. We have a value, say L. We have one value called L. Now we switch up this and get one value. That means we get L2. So you have to find out L1. What could be the value of L1? There could be a lot of combinations within a factory or industry floor. Because if you visit any factory or any industry, then you'll be seeing, it is an ideal condition. If it is a shop floor, then there will be an array of machines at different locations. And when a person moves, then what happens? Depending on the location, moving point, the values received, sound pressure level received from different machines also changes. When you are here, then the sound pressures will be like this added. So it's a continuously varying thing because the point of receptions are varying. So this is a key concept in mapping of noise in a particular given area. We will learn this in environmental noise propagation in details, but the necessity or objective of this kind of exercise is now explained to you. Now let's go back to application, simple application, and so that you can practice it and don't make a mistake during your exams. Yeah, please do it quickly. Very simple, but you must know it. Otherwise, what happens when you go to complicated things, then it becomes difficult to remember. Right. अरे आनंद, तुम कर दिया इतना जल्दी?
हाँ सर.
इतना फास्ट? तुम्हारे पास प्रोग्राम है क्या कुछ?
नहीं सर.
तुम कहीं एक्सेल में बना के रखा होगा?
नहीं सर, ऐसा कुछ नहीं है.
इतना फास्ट कैसे हो सकता है बोलो? अच्छा, इसमें कैलकुलेटर में अमन राज, निहारिका, निहारिका तो न्यू, Wakil is old, Palas is new, and the values are all same. Very good. Actually, there is nothing in it. It is only to check and only to give you a scope for practicing, so that you never forget throughout your life. Very simple calculation. It's a good, interesting thing. Hemant, Siddhi Reddy, Suham Kumar, Purusharth, Arnab. Arnab, you are in second year or you are?
So fourth year dual degree.
Fourth year?
Yes, sir.
And mining department?
Yes.
Okay. So it is open to fourth year also, this course?
I took it as BTP equivalent.
Acha. It's a kind of substitute of BTP, isn't it?
Yes, sir.
All right. Good choice you have done. But do it seriously.
Okay, sir.
BTP in online mode is very difficult nowadays, very, very difficult for the students and also for the teachers. So taking a subject is rather you can concentrate much, much better. Okay, I'm happy that you all are doing and you are doing it correctly. Right. There are other methods also, but I am not. I will share this thing. You can study all these finer things. Now, the sound pressure level measured at a particular location in a factory with a noisy machine operating nearby is 92 dB. When the machine is turned off, the sound pressure level measured at the same location is 88 dB. What is the sound pressure level due to the machine alone? फिर से आनंद कुछ you made some Excel file मुझे लगता है 89.79 Arnab Bala Rajesh Kumar Singh. Okay, go on doing it. So 92 dB and so 88 plus 89.79 gives us 92 dB. Aniket 89. Please all verify, quickly verify. That gives you an advantage of doing this because in my exams, I change the values. The questions are more or less same. Only thing I give separate values. So you will have to do it. Some mechanism has to be there to do it correctly. Otherwise, unnecessarily you'll be delaying, and your submission will be late. Have you got a copy of this book? Soft copy, everybody?
Yes, sir.
Yes, sir.
So you can think of, I will give you certain assignments where, this book will be very, very useful. From different chapters, you will be required to make certain presentations. Not only this book, this is of course one of the best books available, but we'll be having more books also for you. And from here, you can have most of the ideas and details also. What we are talking is today, whatever we are talking about is about incoherent sounds, which is environmental sound. But in laboratory condition, there will be coherent sound. That means the sounds in phase, same phase. So there the complications are actually more difficult. I mean, the complications are more. And these simple calculations, as we do in case of incoherent sound, is not applicable there. So it's not a part of our curriculum, but you can, if you are interested, you can read that part where the coherent sounds are added and what complications can arise. I would say here, I think we have discussed this and these things. Okay. Okay, this is a variation of the similar problem. The company regulation, say this is industrial problem. So in, say we have one company regulation in a country, limit factory sound pressure level exposure at 90 dB for an 8-hour day. This in our country also we have the same thing, that for 8 hours we cannot expose somebody more than 90 dB. That is the danger limit. So 85 dB is the safe one. So that will come later. Now 90 dB. Now already, you know, in a given factory, the current level of exposure is 88 dB. Due to whatever machines, you know, we have 88 dB. That means our limit is, you know, we can go up to 90 dB only. So for this case, what is the maximum sound pressure level that a new machine may emit, so as not to exceed the legal limit, the regulation. So what will be the maximum value allowable by that machine, new machine, so that the total exposure does not exceed the legal limit. It's the same thing, same, you know, old wine in new bottle. That means you have now learned the art of calculation of these things, addition and subtraction, all these things. So when you are working, as some people are working as industrial hygienist or environmental, or the engineers or manager in charge of the environmental pollution control, then you need to have these basic ideas. That's why we have termed this your subject. We call it the industrial noise and vibration. It is more or less, you know, centered around the workings of the industry. Now we'll close this and open the other one. Let's talk something about frequency today. Tomorrow we'll have detailed discussion on this. So any propagating sound wave has been described either as an undefined disturbance, perturbation, or as a single frequency disturbance. There are two options. That means the perturbation or disturbance in the medium, the oscillation from a central reference point, can be either an undefined disturbance, that means not very regular and so many combination of waves. There is some noise is coming. Can you mute? Yeah, Anup, can you please mute? Right, thank you. Now here just a minute. Right. So So either we have an undefined disturbance kind of perturbation, very random, or it can be a single frequency oscillation also. So our range of interest is 20 hertz to 20 kilohertz. Our range of interest. Our range of interest in the sense that we are not pure acoustics engineers. We are actually trying to understand the implication of the exposure to noise in industrial setups. So our importance is directed towards human response. And as I have told right in the beginning of the class, that our range of interest is from 20 hertz to 20 kilohertz. So it is not exactly 20 hertz, and if you 99.19.99 that somebody will not listen is wrong. So you can, there are evidences that you'll be listening at 16 hertz also. The average human hearing range, the frequency range, is spread over 20 to 20K. That is the essence of this particular slide. Now this undefined disturbance may be described conveniently as composed of narrow frequency bands. That means there are a collection of frequencies each characterized by a range of frequencies. That means we can divide the entire spectrum. We can divide the entire spectrum in smaller bands. And each band is composed of several individual components. Not necessarily that those several components, subcomponents, will be present in this band, but subband, but if this and this is present, then we will consider that these frequencies are present in this particular subband. That means it is not necessarily that the broadband sound will constitute of all frequencies, but there will be some of them will be missing also. And another thing is that all the frequencies will not have the same amplitude. That means in frequency domain, if we plot frequency in this and amplitude in this from a broadband sound, then what we'll see, there will be an envelope kind of thing that may be like this. That means frequency versus amplitude graph will give you the distribution of the energy along the different frequencies. It is a collection of frequencies. So in practice, in real life, we have different range of frequencies. Not only that, different amplitude assigned to different frequencies. So that is why our voices are different, because we have not only have different frequencies, but individual frequencies have different amplitudes. So that's why our voices are different. We can manipulate this. If I record this frequency, record this voice through a microphone, then manipulate in an equalizer. We let us know the equalizer means, where you can see the components and then manipulate it. You can do it FFT, and then you use an equalizer, manipulate the frequencies, and the output will be different. That means if Arnab Bala sings, today's computer can transform him into Arijit Singh very simply, without any problem. Not only that, today's you will see most of the singers sings without any fault if their recordings are commercially produced. If the recording is commercially produced, their frequency, जैसे हम पहले बोलते थे सुर में नहीं गाते हैं, मतलब कि somewhere he has lost the tune, maybe some particular note he has missed or not properly sang. So how do we manage that? What we can do with this particular frequency analysis, that if I feed a computer with my notations, then it is known then that during singing, what will be the frequency distribution? Say what will be the frequency distribution? Now, in that case, if someone is the real song, in case the real song is being played and being recorded, and if it does not match with this spectrum, we can forcibly match the real singer with the notation. That is possible. And that is why we can do the corrections, and in commercial productions, the notes are absolutely perfect. And with some other enhancements, nowadays recordings are probably the best in the history of acoustics. All the sounds are so beautifully, done, because it is highly manipulated by the recording engineers. Now, it is customary to refer to a spectral density level when the measurement band is 1 Hz wide, say 2 1/3 octave band or 1/3 octave or octave band level. So we can have just measurement of 1 Hz means 1 Hz, then 2, 3, 4, like a huge number you can do. Or what you can do, you can divide the 20 Hz to 20 kilohertz in say 11 or 10 bands, and you define them as 1 octave band. 1 octave band. So 1 octave band. So what is this octave what do you mean by 1 octave? So other than the MTech students, others, please answer, second year. Any idea about the octave? Any idea? No. What is an octave? In real life, you must have used this many times. Many of you are singers, and you know what do I mean by octaves. Try to remember your harmonium. 1 second. Keyboard. Okay, so wait, okay. So 256 Hertz is our SA. Let me start with that. 256. So can you hear the sound?
Yes, sir. Yes,
Yeah.
sir.
This is the famous SA. SA in our harmonium. SA. And the next octave means when we go to the double frequency, just double it. So at one end is SA, the other end is SA, means just double it, just double it. So 1 octave band means that the upper frequency is double the lower frequency. So what will be the double frequency here? Can you hear the upper frequency?
Yes, sir.
Yes.
Yes, it is 512 hertz. It is just one octave up. That means on the upper side of the upper end of the octave. Let's go back to the lower side once again. Just to, yeah, this is the lower side of the octave band, 256. So sa, re, ga, ma, pa, dha, ni, sa means 8. So that's why we call it an octave. This is in 8 parts. It is distributed in 8 parts. 256, and then we go to 512, just above it. 512. Yeah. And then you go one octave up once again. Am I correct? 1024?
Yes, sir.
That is one octave up. One octave up. Okay, let me stop it. Otherwise, Yeah, so fine. So this is basically the first we went one octave up and then another octave up. So that is how the concept of octave we use in the musical notes. So what we can do that we divide. Please write down these things, and we'll have discussion further and some assignments on this. So you write down that octave band and 1/3 octave band. Try to just Google it and read about these things, how the octave band concepts have been implemented in analytical acoustics. That means in the frequency spectrum part, how these concepts have been utilized. Now, if I rather divide the spectrum that I have recorded into different measurement bands, and if the upper frequency is double the lower frequency, then we can say that the sound spectrum that I have recorded has been divided into octave bands. We have divided that into octave bands. We have divided the entire thing in a series of octave bands. Series of octave bands. Okay. And what will happen that if I try to express the sound that I have recorded in terms of octave bands, and if these are my frequencies, like if this one, the lowest one is F1, then this will be twice F1, then this will be 4 times F1, this will be 8 times F1, this will be 16 times F1. So if I average that energy or the amplitude that we have, then we will have graphs like this, which is very common in equalizers. In mobile phones also you can see that this kind of dancing bars will be there. That means this part is actually showing not an individual frequency, but actually the average amplitude, overall average amplitude of the frequencies present within this band. When these are changing, these bars are dancing. This is a dancing histogram, dancing bar, dancing bar. If you are not satisfied with this, that if you want more descriptor, I mean more, what should I say? We more detailed information. If I want to know more detailed information, that means what exactly happened between this point and this point. Instead of having an average value, can we have further divisions within this? Can we have further division within this so that we can get another graph like this here within this particular band? If I divide it in 3 further subdivisions, then we actually create 1/3. This is 1 by 1 octave band, where the band limits are 1 octave away from each other. But in case we subdivide the bands, then we call it 1/3 octave band. 1/3 octave band, which is having a tremendous application in our acoustics, the measurements and different purpose. for for calculating the powers in one-third octave band. I mean quite detailed, but there are many cases in the beginning when people used to have half octave band also, but this is not popular. This is neither good nor bad. So what we do, either for broad calculations, we go for 1 by 1 octave band, or for detailed calculation, we go for one-third octave band analysis. One-third octave band analysis. In one-third octave band, what happens that you get more information about the frequency components of a particular sound. That means, say here we have a sound wave. We have a single tone frequency like F1. It will show only F1, and the value P is equal to this value. That means here, if you now show it in a oscilloscope, then you will see against the frequency, this particular frequency, you have a single line. That means you are actually seeing a single frequency amplitude against a simple frequency. Now here there is a combination of the frequencies. That's why it's a complex wave. So here what happens? We we now get multiple component, F1, F2, F3, like that. That means disturbance P, so number one, is varies sinusoidally with time t at a single frequency F1, as in B. So now this is sinusoidal wave, so we get the corresponding single line diagram. So here, but see here what disturbance P varies cyclically. This is cyclic. From here it is repeated constantly. If you look at this point and this point, then it's a repetition of these things. Now, now this is a combination of three sinusoidal disturbances of fixed relative amplitudes and phases. So after some times you will see that same thing is repeated. Same thing is repeated in the other part. If you go on seeing it in an oscilloscope, same thing goes on. But it is having three different components. Now what we are doing is that in the next part here, there is much more complicated wave where a number of frequencies are there, where things are not so simply visualized. So here what we do, the disturbance P varies erratically with time t. That means it is not having a particular pattern, repetition, pattern, recurrence. It is not there. So now what we are doing, we are now resolving the entire thing into frequency bands. Say this is our one frequency, this is one frequency 2, this is 3. So in between whatever is there, we are trying to average it and find out what is the relative strength, relative amplitude of the frequency components of the bands that is there. So this is why the frequency bands are extremely useful for the purpose of your analysis of the sound. In the next class, we'll be talking about the random noise and, of course, definitely the importance of one-third octave band, how the frequencies are calculated. This part will be learning tomorrow. Just a minute. So in between, if you have any problem, you will definitely talk to me. And please, read octave band. And one-third octave band. These two topics, how this is decided and what is the component of this, or the end points, the lower part and the upper part of the upper end of the frequency bands. Okay. So is it okay for you? I mean, do you understand things, or could I make it interesting for you? or it's very, online system is very, very tiring. So you try to read certain things from the internet also, that will help you a lot. Right? Thank you very much.
Thank you, sir.
And we'll see you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.